introduction is healing. And so I'm going to talk about curvature flows. Please. Thank you for organizers to give me this wonderful chance to join this wonderful conference. Yeah. So today, well, I'm talk about the curvature flow with free boundary problems, and let me just review a little bit about the degenerate equations. Many of you are familiar with this equation, and the first one is the force medium equation, where the equation will be degenerated whenever u is 0, if m is greater than 1. So it will be degenerated equation if u is 0. And the parabolic P-Laplace equation will be degenerated when the gradient is 0. And now I will mostly talk about the parabolic Monzi-Ampere equation type equation. And then there, u sub t is the determinant of disk of u. Then if you look at the diffusion coefficient, then it will be the second differentials. So whenever the second differential is 0, then equation will be degenerated. So there is a different level of degeneracy, and well, clearly this equation will be very tough to handle. Okay. So now, mostly I will talk about, review a little bit about the nonlinear curvature flows, and then review the known result. And then I will consider three different kind of hypersurface. The first one is a strictly convex case, and next one is a convex one, and third one is non-convex hypersurface. And they do have a different level of difficulties because corresponding operator in different class. So it's the shape of the surface is really related with the class of the operator. Okay. So now let's start with the Gauss curvature, which will be a model equation for the rolling stone. So let's say you start with the certain hypersurface, and then this is a kind of stone, and it's rolling around. Then whenever the surface hits this flat boundary, then there will be a curving happens. So then as you see the stones in the stream, and then you're going to have a very funny shapes of the upstream, but if you go to the downstream, then you...
Are you sure that that stone is going to roll?
Yeah, if you kick it, or it's in the water, then it's rolling. Okay. Yeah, it's okay. So I will tell you it's a little. Okay. Anyway, so speed of the erosion is proportional to the curvature. Let's see this ellipse. So if you give me the same portion of the surface, then I look at the normal directions. So then the erosion happens whenever this surface hits this flat boundary, then there the normal direction matches. So number of normal direction is really related with the speed. So if you give me this semi portion, then you can observe a very small amount of normal directions on this flat part, but you're going to have a lot of normal directions in this sharp portion. And you can observe the amount through this Gauss map. So I look at the ratio of these two areas. This is the amount of the normal directions, and this is the given domain. And then you look at the volume and take a limit, then you end up with the Gauss curvature. So the speed is really related with the size of the Gauss curvature. And now let's look at the mathematical formulation. So we have a hypersurface, and this hypersurface is evolving with this speed, and the speed is proportional to the certain quantity. And this quantity could be the many different one. Sometimes the F could be the mean curvature, then we say it's mean curvature flow, or it could be a Gauss curvature as we observe there. And also the speed may be proportional to the Gauss curvature to the portion alpha, exponent alpha, then we say it's alpha Gauss curvature. And if you look at the sum of the different principal curvatures, then you will end up with the scalar curvature, which is intrinsic curvature. And or you can look at the harmonic mean curvatures, and those curvatures has a different application in the engineering. So you can observe mean curvature flow in the phase transition, Gauss curvature in the rolling stone, and harmonic mean curvature flow in the general relativity. Okay. And then so now this model was proposed by Ferré at 74, and he considered these configurations. So initially, he assumed two things. The flow is smooth. He didn't prove it, he assumed it. And also, initial surface has a lot of symmetries. Then what it showed is if initial surface is convex, then it will be convex forever. And also, it will be a point at a certain time. And this time was computed by Cho. And then he showed, well, if this surface is converging to the point, then he scaled it so that area is 1. Then the shape gets round. And he assumed that the initial surface is symmetry. And then the smoothness of this flow was proved by Cho, 84, and then he used a very beautiful idea about the normal map to compute this time, but then normal map is used to the regulatory theory for the viscosity solution for the parabolic problem, which is maybe different, but is a very important idea. And in 94, Hamilton observed the other things. And if your initial surface has a flat spot, then flat spot will persist for a while if this, well, when this dimension is more than 2. And then Cho and Evans issue showed if two principal curvatures are 0 at one point, then there will be waiting time. And if only one principal curvature is 0, then there is no waiting time. And then the surface will be decomposed into two parts, and the flat part and the strictly convex part, and there is an interface, which is not given. We need to find it and discuss the regularity of it. And this free boundary will propagate with a finite speed. And this finite speed is very important to find out the right regularity across the free boundary. Okay. And then this is somehow, since if we are interested in the regularity around the free boundary, then we just look at this part as a graph and write down the equation in terms of the graph. Then F is the height. Then by simple computations, you can show the Gauss curvature as this equation, which is Monge-Ampère equation type, because if you are close to the free boundary, then gradient of F is almost 0. So then it's pretty close to the Monge-Ampère equation with these error terms. And for the Gauss curvature flow, then you do have alpha, and this alpha will give you different classes operator, depends on the range of the alpha. Okay, so then what is the known result for the alpha Gauss curvature? And let's say your initial surface is strictly convex, then Ben Cho showed, well, all of the picture that I showed is true. And this alpha is very specific, so it's 1 over n. Then operator will be homogeneous degree of 1, and also the operator will be concave operator. So regular theory is rather easy. And then the question arised by Ferré is called the Ferré conjecture. So that means whether the rolling stone will be getting around at final shape. And then that was proved if dimension is 2 by Ben Andrews. And also he considered this alpha Gauss curvature in this range. And this range is very specific, and if alpha is smaller than 1 over n, then operator is a concave operator. So regular theory for the second differential is manageable. And now recently, and one of my students, Lami Kim, and I showed similar result to when alpha is between 1 over n to 1. And then we showed all of those pictures is true except for the ball things. So we just showed the limit profile is a convex and the smooth surface. But we don't know whether it is a ball. And that is the Ferré's conjecture, which is still open. Okay, and then if the surface has a flat spot, then we have some result with the 2D for the Gauss curvature flow. And then for the alpha Gauss curvature flow, well, we have some result with the Lamy and Ungeli. And then also we consider the non-convex surface So if you look at the Rolling Stone that I showed at the beginning, then so the first picture here is harder to roll around, as you know. And then here, so erosion happens when this surface hit this flat spot. So this concave part never look at this part until this one touches here later on. So the interaction between the surface and the flat spot is really interaction between convex envelope of this surface and this bound, this flat spot. So equation become very non-local there. Okay, and also I consider the scalar curvature flow, and then so if sigma 2 is a scalar curvature, and then if you take a half of power, then it's homogeneous of degree 1. This one is also concave operator, and Bencho got the result. And for the standard sigma 2, then we don't have half, then it's not a convex node, a concave operator. So we get some result with the Lamy. And also now we have another result when we have this anisotropic terms. So this term depends on the position. So this one is a really interaction between the surface and the environment. So then still we get some result there. And then the interesting part of this the following. So like we ask the convexity or C11 regularly, then that is really related with the geometric quantities. And then, for example, if your Gauss curvature is positive from the beginning all the way to now, then all principal curvatures will be positive. That means it's convexity. And if you are able to show mean curvature is bounded, and let's say it is convex, then all principal curvatures will be bounded, then it's a C11 estimated. So somehow controlling curvature is really like a regular theory for the nonlinear equation. Okay. And then, so if you look at the alpha Gauss curvature flow, then if you try to look at all of the geometric quantities, then you end up with the full of the equations. So you don't need to understand it, but it's just messy. That's enough. And the thing is, if you look at the third differentials, if you look at the second differential, so this is a second fundamental form, then it will satisfy some equation. Then this is the third derivative, which is not a positive nor the negative. That is the difficulty for these operators. Okay, so now this is the my result.
Let's understand that. Could you go back?
Yeah.
So what is Hij?
Hij is a second fundamental form. And the Gij is metric. This is normal direction. This is Gauss curvature, and this is mean curvature. Yeah. So basically, we want to get information. Then we mix these quantities to track down the information. Yeah. And then this is the result for the strictly convex case. But basically, what it says is the following. Like, so there are lots of things, but let me show you the information. So the first part is saying that if you have an initial surface, then you will converge to one point at a certain time. There is no thin things, so just one point. And the other part is, and then if you use scale, the picture so that the area is 1, then it will converge to certain manifold, convex manifold in C-infinity fashion. And also, if you look at the limit profile, then limit profile can be written in terms of a support function because it is a convex function. Then the support function will satisfy elliptic equation. So in the other words, the limit profile will satisfy elliptic kind of eigenvalue problems. But it is nonlinear eigenvalue problem. And also, the fourth part is all of the principal curvatures is order 1. It means the final profile is not a thin things, it's just a finite good shape. And that's it. Okay. So to do these things, I briefly review what I did. And then strictly convexity, so there are two parts. So before blow up, in the other words, before it becomes 1 point, there is a regular theory. And the first one is a strict convexity can be shown, the positivity of the Gauss curvature. And also we showed that this Gauss curvature is bounded above by looking at the evolution equation of this quantity. And we showed that this is bounded, so Gauss curvature is finite. And the other part is the C11 estimator. So if you can show the mean curvature is bounded, then every eigenvalue, every principal curvature will be bounded above. But the problem is that this mean curvature equation doesn't follow good equation, so that we can apply maximum principle. So all of the question is we want to know something. We know the quantity, but the question is whether this quantity satisfies the maximum principle. So we need to create new quantities to tell the story. So then we look at this quantity. So this is a sum of the inverse of the principal curvatures. And we show this quantity really satisfies maximum principle. And if we are able to show the upper bound of this one, then so all of these quantities is positive. So in the other words, if 1 over lambda 1, let's say this is the minimum principal curvature, then this one is bounded. In the other words, minimum principal curvature is bounded below by this estimate. We can show this part. And also the multiple of the order of the principal curvature is bounded above from this one, then we can show this. Sorry, this is max. Okay, this 2-1 will give you us this estimate, and then we get a smooth solution through the regular
C
theory.
satisfies the maximum principle even if you don't have the inverse harmonic flow.
No, yeah, for the alpha Gauss curvature flow, for their range, and this quantity has a maximum principle. So we are very released. At the beginning, we spend a lot of time to try different quantities. Yeah. Anyway. And then now the blow profiles. So then we need a monotone quantity. And then, so this quantity is known by Fire, he used it, and then we constructed a different quantity for alpha Gauss curvature flow. And whenever you try to create a monotone quantity, the divergence structure of operator is very important to make an integration by part. And this Monzon operator is fully nonlinear, but it's very interestingly, it has a divergence structure. Yeah. So then we can use that structure to show this one is monotone. And then we use this monotone quantity to show the limit profile is a good one, not like thin things. Okay, how can it do? So basically we used John's lemma and affine transformation. So John's lemma says if you have a convex body, then you can put a ball inside and the ball outside, and which is have the same ratio. And then also affine transform says if you have a ball, then through the affine transform you can make an ellipse. So these two things basically tells you if I have a surface, then I can put the ellipse and the other ellipse, which is a multiple of the previous ellipse with this amount. Okay. So now, if final configuration of, let's say this one has a very thin things. So let's say if funny thing happens, then the maximum width and the maximum width will be much larger than minimum one. Then ellipse will be very distorted. Then we computed this integral quantity for this ellipse, then this one goes to very large. But we showed that this is monotonically decreasing. So initially it was finite, in future it is finite. But if the surface is has a very funny shape, then this quantity goes to infinity, so it's a contradiction. So that's one of the way to control the width. Then if you have a control width, then you can control the other things later. Okay, so this is the story for the strictly convex case. And now let's look at the just a convex case with a flat spot. Then here we do have a free boundary, and let's say this is the position of the free boundary. So gamma of t is the position of free boundary, and this is our equation. So now we try to look at what is the optimal regularity, which we don't know at the beginning, but what you know is the following. So if you look at the free boundary, let's say the speed of free boundary is infinity, then we cannot see the free boundary, right? And if free boundary, the speed of free boundary is 0, then there is no regularization effect. So if we expect a regularization effect and free boundary, then the speed of free boundary should be order 1. So that's our observation in the picture. So now that is clearly related with the regularity of the surface. So f is 0 under the free boundary. You take a time differential, then you do have this one. Then the speed of free boundary is minus f sub t over gradient. So we do have this relationship if it is a rotation symmetry. And now let's say f sub first differential has this shape. So S is the distance from the free boundary, and let's say it has a power beta, which we don't know yet, and plug this number in the equation, look at the orders, then the speed is order 1. It means this exponent should be 0. From there, we find beta. So in other words, if we expect the free boundary has a finite speed and non-degenerate speed, then the first differential should have this profile with this beta. And this beta goes to infinity if alpha is 1 over n. So in other words, if alpha is smaller than 1 over n, the speed is infinity. In other words, there is no free boundary. Okay. So, so that is the existence of free boundary if alpha is greater than 1 over n. And if dimension is 2 and alpha is 1, that is the case which is considered by Ben Andrews, then beta is 1. If beta is 1, then first differential is 1, so therefore f is s squared, so the optimal regularity is C11. And if you consider different dimensions, then you do have exponent which is smaller than 1, so optimal regularity is not C11, it's a C1 beta, which is very hard to control, because C11 can be controlled if you know the upper bound of mean curvature, but now mean curvature is infinite all the time. So that's the open part. Okay.
I mean, when you say it is not, I mean, you don't know.
Yeah, we are studying now. So I need to, Gauss curvature goes to 0, mean curvature goes to infinity. I need to mix some quantity. But the question is whether this quantity satisfies maximum principle. Okay. So then to understand the regularity, we use the ideal pressure in the porous medium equation. If you have a different n, then you have different profiles, which is Holder fashion. So if you want to consider the regularity, you look at the pressure. Pressure normalize the pictures. So every pressure has a linear behavior to the free boundary. And that is the right quantity where we can find the regularity. So we look at this pressure like a function which is a linear behavior. Then we look at the equation for this G, and then it has more terms. And then, so let me tell you another story. Well, if you have a flat spot and the dimension 2 alpha is 1 standard Gauss curvature, then the solution is quadratic across the free boundary. But if you approach it to one point, it's a flat spot goes to one point, then speed accelerate, and then there will be improvement of the regularity, which is C2 delta. And then we get an estimate for delta. And for the Monzon equation, there is a scaling invariance. So we show the uniqueness of this alpha for the parabolic Monzon equation. Okay. And for the Gauss curvature flow with a non-convex surface, so we consider the rotation symmetry case, and there is a concave part. And then, so there is a free boundary interface between this concave part and convex part. In the flat part, flat problem, this one is moving inward with the same level, so it's easy to control, but this one is moving upward. So it has a different regularity. So I follow the same argument saying that the speed should be order 1. From there, we got an optimal regularity. So first differential has this order. So regularity is exactly C1, 1 over n. And then
this is a conjecture or a proof?
It is proved for 1D. And the higher dimension is conjecture. Or maybe Kiam's conjecture. I never conjecture. So then the interesting thing is right here. So this is a really non-local equation, which is very difficult. But in this rotation symmetric case, the first differential is 0. So I look at the equation for the first differentials, and free boundary is where the first differential is 0. So I look at the equation, and then we have a very nonlinear equation, which is a very similar flavor with the P-Laplacian. And under the boundary, we have a nonlinear free boundary condition. But when I look at it, this one is like a Stepan type. It's very interesting. And we get this C1 alpha regulated for the non-convex surface. And this is a simple summary of the classification of problems. So we consider the surface, which is strictly convex, convex, and non-convex. And here, this one is the equation is non-degenerate. This is this is not concave. So this, if it is, yeah, this is not. This is a mistake. And this is not degenerated equation. So if you get a C11 estimate, it will be uniformly parabolic. And for this problem, we do have a flat spot, so equation will be degenerate. And non-convex case, you look at the convex envelope of the surface, so it is even non-local equation. And then to show the theorem, so let me briefly, what is the theorem? So there is a conditions. Initial condition means basically your initial free boundary is moving with finite speed and non-degenerate speed. And that's what it says. It has a lot, but anyway, the initial speed of free boundary is finite and non-degenerate. That's the condition. Then the free boundary will be smooth, and surface is smooth up to the free boundary. And that's the result. And then to look at it, basically getting an optimal regularity, all of them. And so let me, yeah, basically the question is getting all of the optimal regularity of each quantities. And so the steps is pretty clear. The first step is getting a rough idea of the speed of free boundary. And how to get it? Well, this is a degenerated operator. It's harder to construct barriers. So one of the way to construct a barrier is you rescale your original solution. And that is still satisfies same equation. You compare it, then you can track down the speed of free boundary. And that's what it says. From that information, you can have a gradient estimate of the pressure-like solution. Because the pressure-like solution has a linear behavior, and gradient estimate really tells you optimal regularity. And also, the harder part is the upper bound of the tangential secondary differentials, which is order 1. So we look at this quantity and get the very tough equation, and we get an upper bound. And also the lower bound of the second differential comes from this estimate. And this is pretty close to Aronson-Benillan estimate for the Peirce medium equation. So there, Laplace of V is bounded below. Now this second differential is bounded, and we look at this quantity, and we are able to show it. That's it. Thank you.
So for this result, you need to have a strict convex case.
Well, strictly convex case. Basically, we showed everything except for the ball, and that is still open problem known as a Fourier conjecture.
What is the difficulty in going from the convex shape to the ball?
The difficulty is basically, if you look at the nonlinear eigenvalue problem, Laplace of u equal to minus u to the p. If p is greater than 1, the uniqueness of the ground state is open problem, right? And this is a nonlinear equation for the Monzon equation. And then it has the same superlinear case. So it has parallel difficulties.
It's a question of non-uniqueness.
Non-unique. Yeah, we don't know the uniqueness of the elliptic solution. Yeah.